Stay strong.
Stay safe.
Stay safe. Stay safe.
Stay safe.
Stay safe.
Stay safe, everyone.
Stay together.
Stay hydrated. Stay strong. Stay safe. Stay at home. Stay at home, yeah. Stay at home.
くれぐれもお体をお大事に。
Good afternoon, everyone. I'm Casey here again, and on behalf of IK Academy, I would like to welcome everyone from different part of the world to our webinar Learn with IK Live series. I'm seeing some audience from Thailand, Malaysia, and Philippines. Hi, everyone, and you may wanted to share with us in the comment section. Hi, and where are you from? Okay, before we start, can everyone please help me to comment hashtag IK Academy so that I know you are here? And also please help to share this with all your friends and colleagues that they need the content of it. Okay, for those who are new, IK Academy is a technical training provider. For those who first heard about IK today, IK stands for Integrating Knowledge. We train, we integrate. We help technical professionals across the world to integrate what they have learned into their professional and personal lives. This is important because we believe that the correct technical know how can save lives. All it takes is just the push of a wrong button. Neutrality is our priority. Rest assured that we are a totally brand neutral with a strict focus on education. Why? Because we know your next course of decision depends on it. Drawing from decades of experience, our network of industry experts will bring practical wisdom to solutions. No textbooks, only experience. Our training programs cover maintenance, PV solar, waste, building facilities, electrical, energy efficiency, and more. The mode of trainings that we offer includes online, offline, and hybrid sessions. It's either public or customized in-house. We at IK Academy are committed to provide the best learning experience to all our participants. We believe learning is a lifelong process. Give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime. And I'm happy to see some students here to learn with us in this webinar. If you wish to get more information of IK upcoming trainings from April to August, please click on the link below and fill up a simple form. Our team will contact you further. Okay, now let's proceed with our agenda of today. Before that, please like and share this live webinar who you think will be interested with our sharing today. You may click the share button and share it directly through your Facebook page or LinkedIn, or you may share it around the WhatsApp, Telegram, or any medium that you find may convenience to you. And remember to type hashtag IK Academy to show your support here. I would appreciate that. Okay, today we are glad to invite Dr. Lal from Singapore to share with us the topic energy optimization of clean room. A clean room is an enclosed space with a lower level of pollutants compared to the external environment and where various space conditions are maintained within control limits. Clean rooms are necessary for various kinds of manufacturing, medical, and research spaces that require particle and bacteria-free environments. Some typical manufacturing facilities that use clean rooms are in semiconductor, pharmaceutical, and aerospace industries. Contamination in such environments is prevented or minimized by multiple strategies such as filtration, dilution, process exhaust, and various design aspects. All these features result in high energy consumption by the air circulation fans and air conditioning cooling systems. This webinar aims to provide an introduction to clean rooms and will describe the main sources of contamination and how they can be mitigated. Finally, various optimization measures that can be utilized to minimize energy usage in clean rooms will also be explained. Dr. Lal Jayamaha is the author of two books on energy efficiency titled Energy Efficient Building Systems and Energy Efficient Industrial Systems, and the founder of LJ Energy, which is one of the leading energy services companies with offices in Singapore, Malaysia, and Sri Lanka. He graduated from Queen Mary College, University of London, with a first-class honours degree in mechanical engineering in 1982. In 1990, he was awarded a research scholarship by the National University of Singapore to undertake a research leading to a mechanical engineering degree. After completing his master's degree in 1993, he continued his research in heat transfer relating to building heat gain and building energy performance and was awarded a PhD degree in 1997. After completing his PhD, he specialized in the area of energy management and has been the team leader of many major energy audits and energy retrofits carried out in the Asian region. He is an EEO assessor, qualified energy services specialist, certified energy manager, LEEDAP accredited professional, professional engineer, chartered engineer, GBI facilitators, Green Mark AAP, BCA registered and energy auditor, Green RE manager. He's also the member of Institute of Mechanical Engineers UK and the American Society for Refrigerating and Air Conditioning Engineers. Let's begin with the webinar live today with Dr. Lau, all the way from Singapore. Okay, Dr. Lau, you may
Yeah,
out your
hi.
presentation.
Yeah, Casey, thanks for the introduction.
Yeah, no problem.
So let me share the presentation slides.
Yep.
Okay. Okay. So good afternoon to all of you, wherever you are. I think it's afternoon wherever you are because you're all mainly from in Asia. So today I'm going to talk about this energy optimization of clean rooms, right? So when we say energy optimization, we are looking at how to reduce energy consumption. Not the clean room. It's because the clean room doesn't consume energy. It is the systems associated with clean rooms that are systems that are required to maintain a space clean. Those consume energy, and we are looking at how to minimize the energy consumption. So in this short webinar, these are the main areas I will cover. First is I'll provide a brief introduction to clean rooms in case you are not familiar. I'll also look at clean room classification, the most commonly used. There are two commonly used classifications. Then what are the principles or strategies that are used to minimize contamination, to keep a space clean? Then for such a space, what are the main energy consuming systems? And then once you know that, what are the energy optimization measures, which I will just list because there won't be enough time to go through all in detail, but I will go through list and then briefly explain those to you. Okay, so we start off with what is a clean room, right? So clean room, any space can be a clean room. Basically, a clean room can be defined as a space which is it has to be enclosed space. It cannot be open space because you cannot maintain a space clean. It cannot be outdoor, so it has to be an indoor. It's an enclosed space where the internal space is controlled within a certain limits for in terms of contamination. When you say clean space, it cannot be perfectly clean where there are no contaminants at all. So it will be a space which has less contaminants than the external surrounding environment, and where it is all the contaminants and other parameters are controlled within a limit. Okay, so just to illustrate that, so a clean room, as I said, it cannot be external. It has to be within an enclosure, so inside a building. And then it also has to be in a separate enclosure, because if the whole building is a clean space, it will be very difficult to maintain the clean space, because you will have doors, windows, and contaminants coming in, and it will be a very big volume that you are trying to maintain. So normally it is a separately enclosed space within a building, a clean space. So this is a clean room or clean environment, and where the pollutant levels are controlled. So the most commonly the control pollutants are the particles, so like dust particles in a volume of air, or the bacteria, right? So it depends on the process of what application you're using the clean space. In addition to these two main pollutants, usually other parameters are also controlled within a space. So temperature and relative humidity. Right? So the space condition you need to maintain is because there are people working inside, so you need to have a comfortable space. Then also you want to prevent like mold growth, fungus growth, all this. So you have to maintain the relative humidity within a certain range. Air velocity, you also need to maintain the air velocity to prevent stagnant zones inside the clean room where dust or any particle can accumulate. So you need to have a certain air velocity, and also you need to have certain airflow patterns, right? Because you want whatever contaminants that are inside or going or generated in a clean space to be removed immediately in a very effective manner. So you need to have various airflow patterns. Then pressure, right? You need to have a pressure control, because if the green color box is a enclosed space, there will always be people going in and coming out. So you need to maintain the contaminants by having a pressure. So usually this can be a higher pressure than the outside, or in some cases this can be a lower pressure. So normally the pressure inside this green box and the surrounding will not be the same. It will be either plus positive or negative pressure with respect to the surrounding. Then you may also control other parameters like noise, vibration, etc. So these are all depends on the individual application. So again, this clean space usually will not be just housed inside the building. Usually you will have another space, intermediate space, a surrounding environment. So the yellow color box is the intermediate space where we are maintaining the environment which is cleaner than the outside environment. So of course you have the first is outside the external environment to the building, right? So this is the first area. So this is the outdoor environment, which is maybe less cleaner, has pollutants. Inside the building will be slightly cleaner, right? Because it's enclosed. Then this will be the intermediate area, the surrounding area that is surrounding the clean space. So this would be the main space, right? Where you are trying to maintain. So as I said, this cannot be outside. This has to be inside the building as well as an area which is relatively cleaner than the outside. So usually this is kind of the arrangement that you will have in a clean space. Okay, where do you use, what are the applications? So clean rooms are necessary for various kinds of manufacturing, right? So very common use of manufacturing like semiconductor manufacturing, pharmaceutical manufacturing, aerospace industry, then medical can be like operating rooms, and various research spaces, various laboratories that are used, right? So these are typical types of clean spaces or clean rooms. So if you look at the main application, one of the most common is in the electronics or semiconductor manufacturing, right? So why do you need a very clean space for the semiconductor manufacturing? So if you are from that industry, of course you will know. If you are not, for example, this image is showing a semiconductor wafer, right? The round wafer, which can be depending on your manufacturing process, 200 millimeter diameter, 300 millimeter diameter. And within that, you can see the small squares. These are all the various, the chips that are produced, right? So each one is one product. And you can see the size of that. So there are so many fit into a 300 millimeter diameter disc. And so in terms of size, right, is very minute. And these are made up of mainly semiconductor materials, right? Where they are having a special, they have special properties where the current can only pass in one direction, right? That's what the basis of semiconductor materials, and they are used to create transistors which are inside this. And the transistors in a chip can be in billions, right? The i7 chip, for example, is supposed to have 4 to 5 billion, not million, billion transistors. So you can imagine the size, right? So it's very minute. So any dust particle, if there is a dust particle that is inside this manufacturing space and goes into this product, it can make this entire product, right, useless. It cannot function. So this is why this kind of space has to be maintained extremely clean during the manufacturing process, right? Because the precision manufacturing and the very small scale product size. Pharmaceutical, so again, various pharmaceutical products are made. They have to be made in sterile and clean spaces. Why? These medication, right? Patients will take in, swallow, can be injected, can be inhaled, can be where various products like contact lenses are manufactured, which come into contact with your eyes. So all these have to manufacture in very clean, sterile environment. So which again require clean rooms or clean spaces for manufacturing. Other one is aerospace, right? So aerospace industry also use clean spaces because of the precision manufacturing of like satellites, missiles, space, electronics, etc. Hospitals, yes, I think this one you will understand, right? In operating room, for example, has to be clean, sterile to prevent contaminants going into a patient, or if a patient is sick and maybe has some kind of disease, also to prevent contamination of the surrounding area. Then other category are research labs. So research labs, there are various types of labs categorized into biological, right? Can be chemical labs, can be animal labs where they do testing on animals, and physical labs where they do testing of lasers, optics, for example. So all these are clean spaces. So used for manufacturing, for medical, like the operating rooms, and for laboratories. So these are the three main applications. And for manufacturing, the most common, I would say, in this region, because aerospace would be limited, would be in semiconductor manufacturing, electronic component manufacturing, and pharmaceutical. Right? So they use these clean spaces. Okay, so now we look at what are the potential contamination sources, right? The most common. So we go back to this green box. We say that is an enclosed clean space. So what are the contaminants that can go in? So basically, when you talk about contaminants, either they should come into the space from outside or be generated within the space. Right? There's only two means of contaminants coming into the space. So how does it come in? So one is supply air, right? Because you need to provide supply air or fresh air into a clean space. Why? Because there are people working inside, so you need to have fresh air. Then you have machines, you have various processes which can also have contamination. Then because of that, you need to have exhaust, right? When you have exhaust air going in, you need to have fresh air coming in to make up for the difference. Because if you don't have, this will become a negative pressure, right? So you need to have supply air. Then you will have people going in, right? The people who operate equipment, right? Run the machine, they have to go in. So contaminants can go in with the people and materials. So you have to take in the raw materials, have to go in, maybe tools that you have to take in, right? Various accessories. So all those can take in contaminants inside. And also infiltration, that means leakage. You can have leakage coming in, right? So these are the potential sources of contaminants going from the outside to the inside. Now, in addition to that, you can also have contaminants being generated within the space. So the particles can be generated within the space, right? So these can be during manufacturing. Right? So manufacturing process itself. In some processes, they use various gases, chemicals, right? All those can be released to the environment and can cause contamination. Then cleaning. So the entire clean space has to be maintained by cleaning periodically. For example, the floor, the walls, the ceiling. So those cleaning materials also can contaminate the environment. And other one is through construction. Right? The construction material used. So that is why you have to use very special materials when you construct a clean room. You cannot use normal materials, right? So if you are using the ceiling board, gypsum board, you have to use a vinyl coated gypsum board. Floor can be PVC, epoxy coated, ceiling can be stainless steel. So you have to use those construction materials that would not contaminate the indoor environment, or at least minimize the contamination, right? So these are basically the sources. So later we'll also refer to this diagram. Okay, so now this is the same diagram, but okay, based on studies, they show that out of all the contaminants, right, contamination sources, the highest contamination is from people. 75% of the contamination is from people going in, coming out, or working inside, right? Why? Because the humans shed skin particles, right? So based on research, they say roughly skin party 100,000 to 900,000 particles per minute is shed by a person working at rest, not moving around. If you move around, these are all published data, say at 2 miles per hour, right? So you can convert this to kilometers per hour. Can be even more than maybe 1 to 5 million, right? Million particles per minute. So you can imagine the amount of contaminants coming out, right? Generated due to the actual people working there. So the rest can be ventilation. Ventilation means is supply air going in, right? Room structure, this is from the construction material and the equipment during the production process. So 75% is from people. Okay, so what are the operating principles? So we already I explained the contaminants either had to come from outside or had to be generated inside. So the key principle or strategy is first is contaminants must not be introduced into the control environment from outside. Right? So this is from going from outside, you are here we are saying it must not go, but of course it is not practically possible to stop completely. So the strategy is to minimize contaminants from going in. Second is for the generation part is to minimize the particle generation within the space. Right? So basically you are trying to minimize contaminants going in and contaminants being generated inside. In addition to that, contaminants must not be allowed to accumulate in control environment. That means you should not have stagnant areas where any contaminants, if it goes in, it should not remain there. So you won't have like a window sill where the dust can settle, right? So you will have very flush surfaces. Similarly, other than being able to prevent this accumulation is to remove as rapidly as possible, right? So that is why the velocity I mentioned, air velocity is very important, airflow patterns. This is to ensure that whatever contaminants that are generated inside or goes in are quickly, rapidly removed from the space. So these are the four main strategies that are used. Okay, with that, now we look at how to control these contaminants, right? Before we talk about energy saving. So because the energy consumption is due to all this, right? All these requirements. So control of contaminants. So first we say there is supply air going in, right? So how do you control the contamination is by filtration, right? So you have special filters. This won't be the normal filter. So you use the HEPA filter, ULPA filter, all this to filter the contaminants. Then for materials, so these are the materials that you take in. First is the selection of material. What material you are able to take into a clean space, right? So if you are working in a clean room environment, you will know like normal paper, you can't take normal paper, you can't take normal pencils, right? You can't just carry anything in. So you have to use special paper, special pens, and even that you have to carry in a special bag, clean room bag. Any tools you take also are controlled. And then other than selection is you have to clean them before you take them. So you pass through air shower or some device to clean, and then that helps to minimize the contamination from materials. Then from people, right? So protective clothing. So as I said, a lot of the contamination is from people. So this is why you will find in the clean room, all the people working are actually wearing protective clothing, right? The gown, the head cover, mask, shoes, all that, gloves. So all this is required to minimize any contaminants or minimize the contamination from people. And not only you have to use all this, it is very important how you put them on, right? There is a particular order how you do the gowning. And when you come out, how you remove them. Then people working there will know that they cannot use perfume, they can't use lipstick, and you can't smoke and just immediately go in. So there are lots of protocols to minimize this contamination through people. Second is air shower. So when you go in, even with all this protection and the gowning, you have to go through an air shower, which will actually clean the outer, whatever contaminants on the outer surface of the body. And you normally go through a airlock or empty room, right? So this would be a separate room through which you go. If you're going in through here, so you won't have a door where you just open and go in, because there can be cross contamination. So you go through a empty room or some device, airlock, where you go in and then both sides are closed. Then there's air shower, it cleans everything, and then this air inside enclosed will be clean, relatively clean. Then this door will open and then you go in, right? So there are this kind of arrangements again to minimize the contamination going in. For internal particle generation, minimizing can be cleaning materials. That means what material you use to clean the surfaces, right? So all the chemicals that you use, even the mop, you can't use a normal mop. So there are specially designed mops which can be used to minimize contamination. Construction materials. So as I said, you can't use normal materials, right? You can use stainless steel, glass, polycarbonate. There are various materials, epoxy coated materials that can be used to minimize contamination. Recirculation. So this is something very important, which also leads to a lot of energy consumption. Recirculation. So whatever particles that are generated here, to remove, we said that you have to prevent it accumulating here, right? And you have to remove as soon as possible. So what is done is there is a Usually there are recirculation systems with fans, right? So there are many fans, they take it and with filter. So this is, they say this is a filter, right? So of course there are many fans, many filters. I'm just drawing a schematically. So this is circulating continuously, a very high volume of air. So it is taking air, it's creating a velocity inside here to prevent any stagnation, and taking all dust particles or whatever contaminants going through this and filtered, and then the cleaner air is supplied. So this is continuously happening, and so this leads to a lot of energy consumption. Right? So we look at this later. Then dedicated exhaust. So if you have machines, so if the machine itself is generating various contaminants, right? If it's in the manufacturing is using some chemicals, gases, all these cannot be released into the clean space. They have to be exhausted out. So there will be exhaust systems, dedicated exhaust systems to exhaust the air out or the contaminants out. And next is the infiltration. So infiltration, as I said, is the leakage part of it, right? So there's a leakage. So how do you minimize this leakage across from the outside to the inside? One is in the construction, right? When you construct the materials, the design to prevent sealing, right? Prevent gaps, joints, and then the other one is the pressure control. So you are maintaining a pressure difference across this, right, between the inside and outside. This depends on your design. This can be positive with respect to this, or it can be the opposite depending on your application, right? So all these are required to minimize to control contamination. Then, okay, to summarize, so as I said, going from outside, right, any contaminants going from outside, so you can go through openings or through the makeup air. And how do you minimize? Sealing, airlock, pressurization, filtration, or from an adjoining room. This is from outside, totally outside. This is from adjoining room. So again, sealing and pressurization. So this again, just a summary. Then for internal people going in, so how do you minimize? Gowning and air shower. Work surface inside, so using suitable furniture. So you can't use, for example, wooden furniture, right? So you have to use special furniture. Various process equipment, having exhaust to remove contaminants. For raw materials, semi-finished products going in, right? So because always you need to have raw material or various semi-finished products going in. So you have to wash and clean them before taking them in and go through an airlock. And then you have local exhaust, right? If you have contaminants such as gases, chemicals, you have separate exhaust systems. Then for cleaning, you use suitable cleaning chemicals, which are not the normal ones, and construction material. Carefully selecting the construction material to minimize contamination. So basically, this part is just summarizing what I explained in the earlier diagram. Okay, now we look at the classification. So when you talk about clean rooms, you can just have a clean space, or you can design and operate it to meet a certain standard, right? So what standard can it be? So of course there can be many standards. Different countries have different standards. I would say the two most common are these two: the ISO standard and the US FED standard, right? So these are the two: 14644-1 and 209E. So the differences, okay? So first we look at the ISO standard. So ISO standard first. It is basically defined based on this size of particle, 0.1 micron, 0.1 micrometer in terms of diameter of the particle, and it is per cubic meter of air, right? And the classification is in a number, ISO 1 to ISO. So it can be, because it's ISO standard, so it's go from 1 to ISO 9. So maybe we say 2, 3, going up to 9, okay? So this is classified based on how many 0.1 particles, micron particles are there per cubic meter, right? So in terms of number, this is 10, this would be 100, this next will be 1000 and going on. Basically, it is this number refers to the 10 to the power. So this will be 10 to the 1 is 10. This 2 is 10 to the 2. Which is 100, right? ISO 3 means 10 to the power of 3, which means 1000. And this will be 10 to the power of 9, right? So that will be the number of particles here. So it's very easy to remember. The ISO number refers to the power of 10 in terms of particles per cubic meter of 0.1 micron. So if you look at this table, so we are saying this is the reference that they use, 0.1, right? So this first column is the one. So you can say ISO 1 is, this is 10 to the 1, right? This is 2 is 10 to the 2 and so on. So up to here is 10 to the 9. Of course, there is also equivalent in different sizes they have for 0.2, 0.3, 0.5 and so on. But easier to go through this because it's very easy to remember the first column, right? So you have to remember its particle size and it's per cubic meter. Because other common standard, the US one, this goes by class, right? So the other one is ISO 1, 2. This is class, can be 1, 10, 100, 1000, and so on, or multiples of 10. Okay. Now the main difference is particle size. The earlier ISO is on 0.1. This is 0.5 micron. And that was cubic meter. This is per cubic foot. So the unit of measure is different, right? So what this means is this number says 10, right? So 10 means there can be 10 or less particles per cubic foot of air, and this size of particle. So 0.5. So here, if it's class 10, you can have 10 or less 0.5 micron particles per cubic foot. 100 will be 100 or less. 1000 will be 1000 or less per cubic foot of this size of particle. Right? So basically, it's a two different ways of defining. This is again, okay, so this is the one we say the reference for this US one is the 0.5, right? So the 0.5 is this one, this column. See, class 1 is 1. You can see this column and this column, numbers are the same because these are reference. Now, if you want at a different particle size, then you will have a different number. And if you remember the ISO is 0.1, right? They are using 0.1 micron size, but ISO is per cubic meter. This is per cubic foot. So the conversion between cubic meter and cubic foot is roughly about 35. Why? Because there are about 35 cubic feet in 1 cubic meter. So ISO 1, remember, for 0.1 is 0.1 micron per cubic meter. So per cubic, so this is in cubic foot, right? So it'll be 35 times. So basically, there's also a comparison table where you can see the equivalent. So basically, ISO 3 is equivalent to the US 1 and so on, right? So these are the direct equivalents, and you can just use this table, or you can just look at the particle, the numbers in the earlier tables, and you will also find their equivalent. Right? So this is just the classification depending on which one you use. Then for the medical, for the pharmaceutical, so depends on which whether you use the US FDA guideline or the EU European guideline. So if you're using the FDA, so you can see, so they're in terms of 0.5 micron per cubic meter, right? So this is a 100, 1000, 10,000, 100,000, right? So these numbers are in terms of cubic meter. If you convert this to try to find out what is equivalent to ISO, this will be ISO 5. This will be ISO 7, and this will be ISO 8, I think. So you can see the equivalent. So if for the sterile products, other than the particle, what is important is a microbiological limit. So they also specified separately the microbiological limit. In this unit, they use the CFU, it's a measure of the contamination, biological contaminants. This is colony forming units, right? So it's a way of measuring. So this column is where they take air, a cubic meter of air, and then they culture the air and let the colonies form, and they count how many are there. This is a different way of doing. They use a 90 millimeter settling plate and take the sample. So you can see, right? So here under classification 100, you can have less than 1, so almost 0. So this has to be very, very clean. When you go down, right, you can have a slightly higher allowable contamination level. So this is for the US standard if you're using it. If you're using the European one, similar, right? So again, so this they also specify, you can see at rest and in operation. So what is the difference? At rest means the clean room environment, all the fans, the filtration, everything is functioning, but there's no manufacturing. The in operation is with everything what manufacturing taking place. So that one you have to maintain. You can see B, grade B, C, and so on, right? I mean, manufacturing, they allow a higher contamination level compared to the non-operating level. Right? So this is how they classify. This is at a different particle size. Right? So this is some just reference data to give you some idea as to what are the classifications and what are the requirements, typical requirements. If you look at the types of clean rooms, so of course they can be in different arrangements. I would say the most common classification would be the so-called ballroom types, bay and chase arrangement, and mini environment. So what are these three? So ballroom these are the very big clean rooms in mainly in semiconductor manufacturing, right? So the so-called ballroom is a very big volume where all their manufacturing process take place, where the clean environment is maintained at a common level. So can be ISO 5 or whatever. And then air is passed through, is filtered, goes through, and there are, of course, underflow. This is to make sure that the airflow pattern, right? You have a linear airflow pattern and a certain velocity that is maintained. Then this air will go in through here and is taken back, filtered, and supplied back again. So this is the recirculation part on the two sides. And then, of course, you have the fresh air coming in. Right? So this is a typical arrangement. It may not be exactly the same arrangement, but this is a typical arrangement where you have very large volume and air is supplied from the top and air is removed at the bottom, and part of it is recirculated back in again. So this is the big one, the ballroom. Second is this the bay and chase is where you have the green color is a clean manufacturing space and the blue color is a service area. So this is where in some of the manufacturing where maybe the equipment you have to go many times to access the machine, to change some part or tool in the manufacturing. So what they will do is they will install the machine like this, where the manufacturing side will be the clean space and where you need to do various changes will be in the service area. Right? So in a lot of the pharmaceutical plant, they use this kind of arrangement. The third one is a mini environment, is a clean room within a clean room. Right? So you have a clean space, but if you want a very stringent space, but you need for a smaller area volume because maybe it's one manufacturing process, you can have a mini environment. So this is just showing a diagram. This can be within the main clean room, right? So you have the air going in and you have all the air coming out, right? So so this will be maintained at a ISO or the US FID class, more stringent than the outside, right? So, but this of course has to be inside a bigger clean room. So this is mini environment. Okay, now we look at the energy consumption, right? So we had to look at what systems consume energy. So we said if this is the clean room, clean space, the green color one, we have where does the contaminants go in? We said from outside and generated inside. So going in first is the supply air, right? We say we need to filter. Then we said, of course, can go in through people and material going in, right? But these two are not related to energy consumption, right? Because you clean them, you select material, they don't result in more energy consumption. But filtration, yes, because you have to supply the air through the filters and based on the volume of air going through. Not only filtration, it's also you have to treat the air, you have to cool it, you have to dehumidify it. So there is energy consumption. Then similarly, infiltration, how do you achieve this minimize is by pressure control, right? That means you are controlling the amount of the pressure inside here, which also will result in energy consumption for the fan. Then you have exhaust going out, which also you have fan energy consumption. And other one is a recirculation, right? You are recirculating a very large volume of air, right? Because you are filtering. So you have the filter, right? You have the filter here, filter. So because of that, this also consume energy. So supply, air, exhaust, recirculation, infiltration, pressure control. And here you also need to maintain a certain velocity inside. Right? So I mentioned, so there can be different design. Either these fans, this fan, this can be used to maintain that, or you will have separate fans here to create the velocity that you require and also the flow pattern. Right? So these are also required. Other one is you have to maintain the space conditions because of the people working, and also to prevent mold growth and so on. You need to maintain the temperature and relative humidity inside. Right? So all these are causing the energy. Basically, energy consumption is due to all these. Right? So now we look at what are the systems that consume energy in this for each one. Okay. So for the supply air filtration, what consumes energy? One is a fan. Why? Because a fan is blowing air through this, through the filter. And cooling. Why? Because this air has to be cooled and dehumidified. Then your exhaust would be fan energy. Similarly, your recirculation is also fan energy, right? So these are the fans and cooling. Inside, to maintain the air velocity and the airflow pattern is fans. You're having many fans, right? Small fans, depending on the design. Infiltration, pressure control is also fans. And then space condition, maintain the temperature and RH, relative humidity, would be your fans to circulate the air, as well as your cooling system, right? Your air conditioning cooling system, like a chiller system. So basically, you can see now there are two categories for energy consumption, right? One is the fans, right? The fans. What are the fans? So one can be the fresh air going in, makeup air. Can be air handling unit, recirculation air handling units. They are also called dry coils, which there's not enough time to explain all this. But basically, these are all in a very big clean room. They will have all this. Then there's this called FFU, fan filter units, right? Very often these are also used. So these have fans, filter units. These are okay. Then exhaust, right? So I would say fans are used for all these, and these result in the fan energy consumption. The other category we said is cooling energy, right? That means a cooling air conditioning energy. So where is that from? Chillers, pumps, cooling towers, right? Because usually you will have central cooling system. So you use chillers, very big chillers, and you have pumps for chill water, condenser water, and then for the cooling towers. So basically these are the two categories. So now finally we look at the energy saving for these two categories. So as I said, there is not enough time to explain one by one in detail. So I will just explain briefly for each one. So first we look at the fans. Okay, so fan, first is ACH. What is this? So this is a term that you will come across in this. ACH refers to air changes per hour. ACH, right? That means if you have a, say this is the volume of the clean room, right? So this will be the, say that this is the width, this is the length of the clean room, and this is the height. So there's a volume, right? So volume is length times width times height. This will be in cubic meters, say, for example. Now, air changes power is how many times you're changing this volume in terms of your fan. So you have fans here, right? So you'll have your fan, and this is circulating air, right? This will have a volume flow rate. This will be in cubic meter per hour. So if I use the same, because this is in per hour, and this I'm saying is in cubic meter, this will be cubic meter per hour, right? So now if your air change, say air change is 200 air changes per hour. And this, your volume, say, is 100 cubic meters, your volume inside your clean room. So your Q will be 100 times 200, right? So it will be 20,000, right? 20,000 cubic meter per hour, or CMH. So this is usually it is defined as a air change. How many times you're changing the air? So it's not physically in that way is measured, but it is, you take the volume of the room, right? And what is your desired air change per hour? This would be your circulation rate for the fan. So this consumes a lot of energy, air change, right? So there is, so the energy saving part is whether you can reduce the air change per hour, right? So normally all design guides will have different air change per hour depending on how clean your clean room has to be, depending on whether it's ISO class 5, 6, 7. So you will design based on that. Maybe for your requirement, it is 400. So you design for 400. Now, when you're actually operating, if you measure the contaminant level here and you find it is very much less than your requirement, maximum value, then that means you can actually reduce this air change rate. So there are some clean room, they have reduced by as much as half the air change rate, right? Gradually, you can optimize by checking the contaminant level and see whether it is much lower than your required value. So based on that, you can actually do the optimization, and air change hour per hour is one of the main energy consumers for the fan energy consumption. Okay, so the next one is this is a base demand based ventilation. This is more applicable for like laboratories, right? Because your demand may change, like daytime, nighttime. In some labs are only operate in the night, daytime, nighttime there is no operation, but you still need to have a minimum ventilation rate, right, to prevent moisture condensation and all that. So you can have a different air change rate daytime and nighttime. Mini environment, which is also what I showed. If you want a very clean space, you can have a separate space, right, within the main one and maintain at a much cleaner contaminant level. Reducing exhaust. So this is like your air change, right? So you can also check your exhaust and see whether you can reduce exhaust. Right? There are cases where the exhaust rate has been reduced by 20–30% because they find that the exhaust flow rate is more than what they require. Again, reduce fan energy. Reducing pressure losses. So this is in your system, your ducting system, in your recirculation system. When the fan is taking air and filtering and blowing back, all the duct sizing, the duct bends, how you construct the ducting, you can all minimize your losses. Then differential pressure control, right? So this is the pressure that I said you have to maintain the pressure within the clean space and the environment, right? This pressure. So this is done by controlling the supply air and the exhaust air. So if you are maintaining, for example, 20 Pascal and you find that you don't need such a high pressure, you can reduce that to maybe 15 Pascal. So what happens? Your fan airflows will reduce. When the fan airflow reduces, your energy consumption will reduce. High efficiency fans and motors. So whatever you are using for this fan here, fans, exhaust fans, all the fans, you can consider using high efficiency fans with the high efficiency motors. And recovering heat in makeup air units. So for the fresh air, normally you have makeup air units, or it's called MAU, where you have outdoor air going in. So the fan is blowing through a cooling coil. So this is the cooling coil. So because you want to maintain a very low RH, relative humidity inside here, so you have to remove a lot of moisture. So when the air comes out here, this may be at a very low temperature, like 8 degrees to 10 degrees, which you cannot supply directly. Then what you have is you have a reheat coil. We increase the temperature to maybe 10 to 12 degrees C, and then you only supply that into this clean room. So you have reheating. So you can minimize this, right? Proper design. For example, you have a separate coil. You can use the return water from this. You can actually send through here, right? So there are many strategies that you can use. So this is on the fan side. And now we look at also for laboratories, you can use a variable air volume, right? So because of the occupancy, operations are continuously changing, but it's not for the bigger spaces, but for the smaller spaces. Then for the central cooling system, right? So one of the most common is the dual temperature chiller system, which a lot of the newer plants will have, but the older plants may not have. Why? Because you have the cooling, you have chillers, right? So these chillers provide cooling for dehumidification. What is dehumidification? Is you reducing the RH and then space cooling. Space cooling, and you have process cooling. Right? So this is supplying both. Now this requires chill water at 5 degrees. This may require only at 10 to 12 degrees. Now, if you know about chiller operation, you will know at low temperature, it becomes very inefficient. So a strategy is to have a separate chiller system, right, to supply only these at 10 degrees. Then this you don't use, you only use for the 5 degree, right? So this is a dual temperature chiller system, which can reduce the chiller energy consumption. Oversizing pumps. So of course, these systems are pumping system. Often the pumps are highly oversized. You can reduce the pump sizing. Reducing system pressure losses, like in the ducting. You can also reduce the pipe pressure losses in the system through design and through optimization. Reducing chill water flow rate. That means in a chiller, you have the chill water going out, chill water supply, and you have chill water return, right? So if this goes at 5 degrees, and ideally this should come at about maybe 11, 12 degrees, depending on your design, right? But now in some cases, you may find this going at 5 and coming back at 7 degrees. your delta T, right? The temperature difference is very low. That means you're actually over pumping. You're wasting a lot of pumping energy. So you can reduce your flow rate. Then the pumps you can use high efficiency pumps, high efficiency motors, and of course, finally, it's on the cooling towers, right? Controlling a cooling tower, fans, speed of the fans in response to the varying load. So I would say these are the main saving measures for fans as well as for cooling system. So to summarize, okay, so clean rooms are spaces maintained at a lower level with a lower level of pollutants and the surrounding environment, right? So this is the basis. It's cleaner than the environment. Use of multiple application, manufacturing, medical, and research. And manufacturing, we said mainly for semiconductor, pharmaceutical, and aerospace industry. Contamination is prevented by minimized by multiple strategies, right? Minimize particles going in, minimize particles being generated, then preventing settling of particles, and to remove the particles or contaminants as soon as possible. So relatively high energy consumption due to contamination control, right? We said to control the contamination, you need a lot of air being recirculated. You need to supply fresh air. You need to supply, remove exhaust. You have to maintain the pressure difference, and you have to continuously filter the air change. So all these result in high fan consumption, and similarly in cooling, right? Cooling and temperature RH control, which also result in chiller energy consumption. So of course, with that, we also went through some optimization measures, right, which are available to minimize energy consumption for both the fans and for the chiller system. So basically, this is all I have at the moment. So as I said at the beginning, this topic has a lot of material to cover. So in such a short period, it's not possible to cover everything. But I hope at least I have given you some idea and some introduction to this topic. So if you are interested further, because we actually do a training, 2-day training, right? So I think IK Academy will probably organize, if you have enough interest from the participants, can organize a 2-day training, which we go into detail on this topic, right? So for the moment, so I will end my presentation and wait for the questions. Thank you.
Okay, thank you, Dr. Lau. Dr. Lau, you may stop sharing your slides.
Yeah.
Okay, thank you very much, Dr. Lau, for the valuable sharing. Okay, before we move on to the Q&A, just in case you are interested to know more about the 2 full days online training on this topic with Dr. Lau, we have an online class on this topic, energy optimizations of clean rooms, which is on the 29th and 30th June. You may scan the barcode or click on the link below, and our team will contact you further. Okay, now we're going to move on to the Q&A. Okay, if you have any questions pertaining anything about this topic or the clean room and energy optimizations, you can actually type it in the comment section. I know currently we're actually streaming through Facebook, LinkedIn, and YouTube. So I will go through it one by one. Okay, before that, because while during the registrations, I collected a few questions as well for Dr. Lau. Dr. Lau, Encik Muhammad Firdaus from Pharma Niaga Manufacturing, he's asking, right, the first question is, are there any options to off or reduce performance of certain main or support equipment for clean room energy efficient?
Okay, so I would say that normally there won't be opportunities to completely switch off, but in terms of optimization can be to reduce, like what I mentioned is, if it is a space that is only operated at certain times, then maybe you can reduce the operation or the airflow, the air changes at certain times when the operation is less, rather than completely shutting off. Because in most cases, they find that it's not possible to totally shut off, because it may, for example, we say for contamination control, you need to have a minimum velocity, prevent pollutants settling down. So if you off it completely, then when you start again, it may be very difficult to achieve the cleanliness you want, right? So you may want to still operate, but at a lower value. So it can be based on some measure, right? Some labs, for example, they use measurement of the pollutants in the exhaust. They measure that, and if the pollutant level is low, then they will reduce the fresh air coming in or the air circulation. When it's high, they will increase it. So this kind of strategies can be used. Yes.
All right, all right. Thanks for your answer. We have another question from Reza Ari from UEM Agenta. So the question will be, is this optimization able to be carried out upfront, which is before the build take place instead of after the clean room has been completed? He understands that the optimization usually is done to accommodate the design issues. But is the system able to design such that actually it can be optimized actively from the start?
Yeah, so I would say actually, usually in optimization, there are two parts. First is in the design, second is in the operation, right? So with the design, you have to make sure you design in such a way that you are also meeting all your design criteria, but you have provision to optimize further. For example, like this variable speed drive, pressure control. So you design it, but you also still need to design within your design parameters. But when in operation, you will find that there is opportunity to reduce your air change rate, your exhaust, then you should have that provision, because if you don't have it, then you maybe need to spend more money to do this. So also the design aspect like this low temperature, medium temperature, dual temperature chiller, your pressure. So of course, designing to minimize pressure losses, using high efficiency pumps, motor, all those are at the design stage, right? Because optimization, you can't really improve it. So for just to give an example, in Singapore now, based on the local regulation, any new manufacturing plant, so semiconductor is one of them, even much smaller plant, it is necessary to go through this exercise to ensure that the design is energy efficient. So all this has to be done and submitted to the authorities. And once they are satisfied that all these have been considered, only will they give approval to construct the plant. So basically, it's very important at the design stage, but also is equally important to optimize while in operation.
Okay, thanks, Dr. Lau. Just in case you have any question, you can actually put it into the comment section. I will go through another few more before we close off this session. Yeah. Okay, the next question will be: are there any specific standard in energy efficient management for clean room applications?
Okay, so for clean rooms, the main standards are the ones that I covered, which are on the classification, the US Fed 1 and ISO. In terms of energy management, energy efficiency, I don't see any standards right now. There was one BS standard many years ago on how to evaluate the energy performance of a clean room, but they have withdrawn that about 10 years ago. So at the moment, there isn't. But I would say, although there are no standards, there are a lot of benchmarking data available, industry benchmarks, right? So especially the semiconductor industry, they have the semi standards where they have benchmarks for each application of supply fresh air, for exhaust air, for air changers. Similarly, various countries, various organizations, internally, they have their own benchmarking. And some of it is published, like in Singapore, the National Environment Agency, they engage third-party consultants to do study, benchmark maybe 10 semiconductor plants locally and overseas, for example. So all these, they have published this benchmarking data. So this kind of data can be used, although there is no standard, because these are actual operating values, right? So they can be used to benchmark your performance and try to improve, optimize using that.
All right, thank you. I think I'll come to the last questions from the floor. What are the main differences when we compare the energy efficiency strategies for common commercial buildings? I think you handle some projects on the commercial buildings as well, and
Yes.
also the clean room facility. So what are the differences?
Okay, so for some are common, like I would say, like using high efficiency chiller, high efficiency pump, reducing pressure losses, high efficiency fans, all these are common. But those others like the air change, these are not encountered in buildings. You don't need to maintain air change. You don't need to maintain exhaust. Of course, you have supply exhaust, but not in the same scale. Pressure control. So all this is not there in commercial buildings. So these are the additional ones which result in a lot of extra energy consumption, right? So mainly the air changes and exhaust and the pressure control and the amount of fresh air that has to be brought in, because you have a lot of exhaust in a clean space, so fresh air, and also the temperature and RH, relative humidity, that has to be maintained. In a commercial building, you may maintain 24 or 25 degree, maybe even up to 70% relative humidity. Clean space, you will normally maintain around 50% RH, and temperature can be lower because of the people inside wearing the gowning and all that. So So these are the differences. I would say, of course, it is more important to consider energy saving in a industrial facility, especially the clean room environment, because energy consumption is relatively much more than in a commercial building.
All right, all right. Thank you very much. I think your answer is very clear for everyone. Yeah. Okay. Before we end, can everyone leave a comment in the social media platform, which is in Facebook, LinkedIn, or even you're viewing this in YouTube? A thank you note to our guest speaker, Dr. Lau from Singapore, and we at least we know that actually we shared something valuable or informative today. And in case right, you would like to go further, that means go in depth for this topic, energy optimization of clean rooms. I think that's a lot much more to cover in these 2 days. So we have an upcoming session on this 29th and 30th June, and you may scan the barcode or click on the link below. We have team to actually contact you later to send you the details. Okay, and not to forget, also to like and follow our page in YouTube, in LinkedIn, and Facebook, and also join our FB community page, iClub by IK Academy, for the latest news for our upcoming IK Live webinar. Actually, we have a lot of series of free sessions ongoing on the content sharing. And our upcoming IK free webinar will be on IK Evening Talk, an interview with Emmeline, the host, what I've learned from growing up with a single parent by Primon, a chemical engineer by profession, on the 12th of April, 8:30 p.m. And there's another webinar upcoming on effective management and recovery strategy for scheduled waste by Mr. Donald Ong and our IK host Diana on the 15th of April, morning session 10 a.m. Okay, that's it for today. And thank you very much, Dr. Lau, for the fruitful sharing. And I hope to see everyone again soon. And this is Casey. Thanks from me. And stay safe, everyone. Bye.
Okay, thank you. Bye.
Thanks, Dr. Lau.
Bye.
Hi everyone.
Hey everyone.
Hello everybody.
Hi everybody.
Hi guys.
Hello everyone.
Stay strong.
Stay strong.
Stay safe.
Stay safe. Stay safe. Stay safe.
Stay safe.
Stay safe everyone.
Safe.
Stay together.
Stay hydrated.
Stay strong. Stay safe. Stay at home.
Stay at home ya.
그- 그래 그래 뭐